Yeah. So good afternoon, everyone. Welcome to this edition of the NITheCS Mini-school. My name is Francesco Petroccione. I'm the interim director of NITheCS, and today I have the pleasure to introduce to you Professor Indekeu from the KU Leuven. Joseph is a professor of theoretical physics, and he works in statistical physics and condensed metaphysics. And today he will speak about one of the areas of relevance to his research. Yeah? Among the many activities of Professor Indekeu, he's the editor-in-chief of Physica A, a renowned and old physics journal. And he's currently in Stellenbosch visiting one of our physics colleagues, Professor Kristian Müller-Nedebock. Yeah. Joseph, please, you're most welcome to start your presentation, and the floor is all yours. Yeah.
Thank you, Francesco. So I hope that everybody can hear me and perhaps also see me. At the moment, I can see just my presentation. So if there is a question or remark, please communicate it in some fashion in the chat, and then somebody will alert me that there is something to be taken care of. So the subject that I would like to address in these lectures is phase transitions and critical phenomena at surfaces and interfaces. So basically, what I'm providing is a kind of guide through this subject from a point of view of very simple modeling and conceptual knowledge. As a background material, I would like to provide the lecture notes of a summer school that I taught at it was actually in Leuven, in Belgium, in 2000, I think it was 2009, and the lecture notes appeared in 2010. And so I will sometimes refer to these notes, but the lectures that I'm giving now are different, in some sense more elementary than those in that paper. So let's start and outline what I will use. I will use notions of classical mechanics, of thermodynamics, and of statistical mechanics. And our approach will be making use of two types of tools. One tool is what I would call a font, which is we are going to find out now together some things. And the other tool is a FOFI. FOFI means find out for yourself. So the FOFI is a kind of homework, and the font is something that we do together during the sessions. So for today, for the next hour and a half, I will concentrate on the problem of contact of phases. So for example, we could look at these pictures here, which are pictures actually of real systems. So I hold one of the systems here in my hand. And if you have a view, you can perhaps see that I'm holding this here. It's a mixture, liquid mixture of methanol, cyclohexane, a little bit of water, and a little bit of blue dye. The methanol-rich phase is the heavier one, and it sits at the bottom of the vessel, of course. The lighter liquid phase is cyclohexane-rich, and the upper phase is basically air with some vapor of these liquids. And what you can see in the picture is that I'm now going to move my cursor also to indicate what you can see. It's a drop of the heavier phase, which is suspended from the upper interface against air. And if you look carefully, you'll see that inside this drop, there is another small drop, which is, as you want to call it, perhaps a counter droplet. And the primary droplet, the big one, is rich in methanol. And also it contains some of the blue dye that dissolves preferentially in the methanol-rich phase. And the counter droplet is in fact rich in cyclohexane. Now, what's interesting in this picture is that these droplets form a contact angle with the upper interface. And so the contact angle in this case is the angle here. And it's, let's say, it's approximately 45 degrees. And you see that the counter droplet makes a contact angle that is 90 degrees plus this 45 degrees. And we're going to study the force equilibria that act on the contact line that where these three phases meet. So we have two liquid phases and one air phase, one vapor phase, and they meet at the common contact line. So here on the picture in the right panel, I have sketched these forces, which are actually interfacial tensions. And you know, an interfacial tension or surface tension is an energy per unit area or a force per unit length. Now, if we consider it to be a force per unit length, then this length is measured along the contact line where the three phases meet. Of that contact line, you can see in these pictures, you can see just only 2 points, one here and one there. And you can imagine the contact line as a circle that is somewhere in this upper interface. So these three arrows here represent forces, mechanical forces, that stem from these surface tensions. And you see that these forces are like vectors that act on the contact line and that pull on the contact line. So for example, the yellow one represents the interfacial tension between the cyclohexane phase and air, and it's pulling the contact line sideways. And so does also the one in light blue, which is due to the interfacial tension between the methanol-rich phase and air. And the red one is the force that comes from the interfacial tension between the two liquid phases. And there is some kind of a force balance, a mechanical force balance here, because the contact line is mechanically in rest. And if these forces would not balance, then the contact line would start to move and the droplet would start to deform. So we're interested now in this balance of forces. And we're going to study this balance of forces in some more detail. Before we do that, I would like to introduce also a second sample, which, as you can see here in this upper picture, does not have a droplet suspended. And the reason it does not have a droplet suspended is that it is a somewhat different mixture than the one with the droplets. And the difference is the water concentration in the liquid phase. So basically, we're looking at two different samples that differ in water concentration, but both samples have a relatively low water concentration and are mainly composed of methanol and cyclohexane. So if we compare these two, then we wonder, why is there no droplet suspended on the left? And there could, of course, be many reasons for that. But the reason that is of interest here for these lectures is that if the system were in equilibrium, and that is not guaranteed a priori, so we will have to equilibrate the system, wait a long time for the diffusion to equilibrate the phases. But let us for a moment suppose that we're looking at equilibrium systems. Then in equilibrium, in the system on the left, it would not be possible to suspend a droplet here, because if we would, the droplet would spread out fully across that entire interface. Whereas on the right, we can suspend a droplet with a particular geometry, with a particular contact angle. And we will see that the contact angle that we can have depends on the water concentration in the sample. But that will come back in a moment. First, I would like to draw attention to the paper of 1980 of Moldover and Kahn that elucidates a phase transition that occurs at the interface that we're studying now, so the interface against air. And the phase transition is called complete to partial wetting. And this will be the primary focus of our lectures, to understand what these terms mean, and also to understand how there can be a transition and even a phase transition between these two regimes. And so basically, if we go to the drawing on the right, we see that we have the two liquids here. We have the picture on the left, which is called the wet state, and the picture on the right, which is called the non-wet state. And I already alluded to the fact that in the non-wet state, we have an articulate droplet. And in the wet state, we don't have a droplet, but we could have a film of the heavier phase suspended at the interface against the vapor. Now, since we are in the gravitational fields, this film of the heavier phase cannot be very thick. Gravity would not associate very heavy penalty of energy if we would try to do that. So the film that is here will thin, and in equilibrium it will be about a few hundred angstroms thick only. Whereas the droplets on the right can have a macroscopic size, and as you have seen here in the photographs, it could be of size of the order of centimeter. So this is our situation, and now we will try to understand these states and also the transition between those states. So looking back at our drawing, I have inserted here a contact angle theta, which is the angle that two of these interfaces make. The upper interface is almost completely flat, not quite. And then there is the liquid interface, which is, as I said, forming a contact angle, which in this picture approximately is 45 degrees, or somewhat more, maybe 60 degrees. And there are several photographs here in the center that elucidate the change of contact angle as we change the composition of the mixture, namely as we change the water concentration in the mixture. And the picture here on the right shows the cosine of this contact angle theta as a function of water concentration. And what we see is that there are several data points here, and also a guide to the eye, a dashed line, which gives us the cosine of the contact angle as a function of water concentration in this liquid mixture, which has at least 3 components, so methanol, cyclohexane, water, and some substance that is the blue dye. And so here we see that the cosine of the contact angle approaches the value unity at some low water concentration. And below that water concentration, the mixture, if we would compose it, would also display a 0 contact angle, would also show what we call a wet state or complete wetting. And so the cosine of the contact angle remains unity for very low water concentrations. And so this is an interesting observation. And we note that the cosine of the contact angle, when we draw a curve as a guide to the eye, appears to have a discontinuity in slope right at a point where we cross over from a non-wet state with finite contact angle to a wet state with 0 contact angle. And so this change of slope, if it is actually real, because we cannot exclude from these sparse data, we could not exclude that perhaps the slope is still continuous if we zoom in on this point. But let's for the moment suppose that the slope is indeed discontinuous, then that will have consequences for the character of the phase transition that we call the wetting transition. So before going on to a more detailed description of the force equilibrium around the contact line where 3 phases meet, I'm going to check whether there is perhaps something going on in the chat or something to be taken care of. So here, okay, I don't see anything that requires immediate attention. So let's go back to the presentation. So here I have sketched a kind of macroscopic viewpoint of the meeting of 3 phases in space. So we call these phases alpha, beta, and gamma. And as we have seen before, these could be liquid or these could be vapor phases. Let's assume for the time being that they are fluid phases, so that the interfaces between them can in principle be deformed and are not rock solid hard. We also distinguish 3 angles, so alpha hat, beta hat, gamma hat, and these are the dihedral angles that span the phases. So now, as you remember, we have some sort of a mechanical equilibrium at the contact line in order for the contact line to remain at rest. And so let's draw the forces on the contact line that act. And so as I have already mentioned, these forces are forces per unit length along the contact line, and they are directed in the direction that the interfaces make very close to the contact line, because these forces are due to the interfacial tensions, which are energies per unit area of the respective interfaces. So this is the mechanical analogy of the effect of the interfacial tensions on the contact line where 3 phases meet. Oh. I have drawn vectors here which are intended to represent force vectors, and they act upon the contact line and are directed away from the contact line. And now comes an interesting point. So suppose we have mechanical equilibrium here, then we know that the sum of these forces should be 0, according to Newton's principles. Otherwise, the contact line will start moving in the direction, presumably, of the net resultant force. Now, there is a triangle that is a triangle in mathematical space, which is called the Neumann triangle. And its sides, the lengths of its sides are proportional to the interfacial tension. So, for example, this side is proportional to the sigma alpha beta, which is the interfacial tension between phases alpha and beta, and so on. And the angles of the triangle are the supplement of the dihedral angles. Now, the question is, how do we go from this mechanical representation of forces on the contact line to the construction of the Neumann triangle? And this is actually something that I'm asking you to do for homework, to be completed by tomorrow, 2 p.m. Derive the Neumann triangle from mechanical force equilibrium. So require the net force to be 0 on the contact line and come up with this geometrical construction as a result of this requirement. And I would like you to recall that the interfacial tension is energy per unit area or force per unit length. And I'm giving a few hints here. There is a down-to-earth way to solve this problem, and that is to use algebraic decomposition into force components, either along 2 orthogonal directions, or maybe along the 3 main directions of this problem. And this is a method of solution for this problem that is used very often and that you will find in textbooks. And it's interesting, it's correct, but it's a little bit of a hard work to do compared to the flying carpet method, which is surprisingly simple and surprisingly not mentioned in most textbooks or documentary materials. And that is to use geometrical and graphical insight and recall the definition of addition of vectors from your standard mathematics. Okay. Good. Once you have completed that exercise, you will notice that in this triangle, as in every triangle, the law of sines and the law of cosines can be applied. And I've written them down explicitly. So for example, the ratio of this side A to the sine of this angle alpha here equals the ratio of B to sine beta and the ratio of C to sine gamma. And there is also a law of cosines, a little bit more complicated, which also you can derive by simply dividing this triangle in a couple of triangles with the 90-degree angle, and then using Pythagoras and so on. So you can very easily derive these relationships. They are useful if you wish to relate the contact angles or the dihedral angles that we had previously to the interfacial tensions. Now, here we come to the essential point of the distinction between wetting and non-wetting. And to understand this, we start from the representation in the upper left, which is the Neumann triangle. And we note that, as in every Catholic triangle, each side is in length less than the sum of the other 2 sides. And so we can quite generally write down this inequality here. that with cyclic permutation pertains to all possible choices of labels. And for example, the interfacial tension between alpha and gamma in this Neumann triangle representation cannot exceed the sum of the interfacial tension between alpha and beta and between beta and gamma. So we can call this the Neumann triangle inequality. And remember that in the homework you're going to do, you're going to prove that the Neumann triangle is equivalent to mechanical equilibrium of the three-phase contact line. So the existence of the Neumann triangle guarantees genuine equilibrium three-phase contact. But if you have genuine equilibrium three-phase contact, the situation is the non-wet situation, where in real space, the three phases meet at a line of common contact, and so do their mutual interfaces. Now, if this is the non-wet state, the question arises then, what would be then the wet state? And the wet state is one in which the equality is satisfied in one particular choice of cyclic permutation of the labels. Not in all of them together, of course, but only in one particular choice. And the choice I've made here is such that if this equality is realized, then the interfacial tension between alpha and gamma actually amounts to the sum of the other two interfacial tensions. But that would be consistent with alpha and gamma not being in direct contact anymore, but being separated by the intruding beta phase, which will prevent alpha and gamma from having direct contact. Now, what happens to the Neumann triangle when such situation arises? Situation that we will call wetting. In fact, we will say that the alpha gamma interface now is wetted by, or wet by, the beta phase. So we're going to find out this now together. What happens to the Neumann triangle when we reach the wetting condition? And I'm going to ask my audience here to reflect on this. You have any idea here, Jane, what would happen to the Neumann triangle when we reach the equality here? It will collapse. It will collapse. Indeed. So the wetting point corresponds to the collapse of the Neumann triangle, and from there on into the wet regime, the Neumann triangle will just remain fully collapsed. Now, there is another part of the homework to be done by tomorrow. Not only you are asked to derive the Neumann triangle from the mechanical force equilibrium at the contact line, but you will be asked one more extra thing, and that is coming now. Suppose we would try to reverse the inequality that we have in the previous slide. So let's go back. Suppose we try to reverse the inequality. So let's assume that one of these interfacial tensions does exceed the sum of the other two interfacial tensions. Let's just suppose that that could be possible. What would be the consequences of such supposition on the force balance at the contact line, and what would be the consequences for the contact line itself if this were the case? So that's the second part of this homework exercise for tomorrow. Now, we're going to move into some theoretical considerations and try to establish a very simple theory, a simple calculation that would permit us to describe a non-wet state to describe a wet state, and also to quantify, using statistical mechanics concepts, the phase transition between the non-wet and the wet state. So the phase transition between the non-wet and the wet state is a phase transition that takes place at the level of the interface between phases. So it is to be distinguished from phase transitions that happen in the bulk of phases. And so let's start from considerations having just two phases and their mutual interface. And also let's recall some of the properties of bulk systems before we dive into the interface structure and phase transitions. So in this cartoon, I have sketched a situation of a fluid, and this could be a liquid vapor system, or this could be a liquid-liquid mixture, in which we have a so-called critical point. Critical point is a point where the two phases become identical to a single phase. And if we, by assumption, would be above the temperature corresponding to this critical point, then we would just have a single homogeneous phase. And so we could describe the single homogeneous phase using some free energy density, that is a free energy per unit volume. And if we plot it as a function of the density in the system, or the concentration in the system, we would locate the equilibrium concentration or density at the minimum of this free energy. Now, a homogeneous state with this particular choice of density would be stable, and it would just have a profile of density versus space that is constant. So this would correspond to a supercritical state or a single phase state. Now, by assumption, below this critical temperature, we can have phase separation into two phases that differ in properties, in particular that differ in density or concentration, as we have seen for the methanol-rich and the cyclohexane-rich phases in our mixture. And so we can describe this with a free energy density that supposedly has two minima. And if the two phases coexist, if they are in equilibrium with one another, which strictly speaking, they are only very close to their mutual interface, then this free energy density would have two equal minima at the respective densities. And the profile of density or concentration as a function of spatial coordinate, a spatial coordinate perpendicular to the interface, would be a profile that has some kind of sigmoid or hyperbolic tangents kind of shape that is drawn here, and it would vary between the density in the A phase and the density in the B phase in some gradual way. So this is the profile of the AB interface. I've called the phases A and B, not alpha and beta, just to be a little bit more independent from the previous notations. So this is the basic picture to keep in mind when we talk about just two phases and their mutual interface, for a situation where either we have the coexistence of two phases that are different, or a situation where the two phases have become identical, respectively below and above their bulk critical point. So coming back to this bulk critical point, there are some properties that we wish to distinguish, and that we will need a little bit later on when we discuss interfacial and wetting phenomena. So I have recapped here the interfacial profile between phases A and B. And I've also indicated some widths of this profile with psi. And we should think of this width psi as being actually quite small. So it could be say, in typical circumstances of liquid-liquid mixtures, it would be less than a micrometer. And it could even be much less than a micrometer. It could even be only like 10 or maybe 50 atomic diameters. So this width is a small length in our fluid. And we will come back to it, because when we approach criticality, this width will undergo some kind of what we call rapid growth. And mathematically, it would actually diverge if we would consider statistical mechanical model of this two-phase system. In practice, even if we would approach a critical point where in a binary mixture the two phases become identical, because of other factors like external fields like gravity, for example, the interfacial width would in practice not exceed a micrometer. But still, a micrometer is enough to see the interfacial fuzziness at criticality in an experiment in the form of critical opalescence. So the liquid mixture, for example, or the liquid vapor system would appear to be a bit milky, because visual light or laser light will get scattered by the density fluctuations or concentration fluctuations, which are of micrometer size, even in a gravitational field close to the criticality. Here on the right, I've just repeated the free energy density with two equal minima. Now, as we approach the critical point, the density difference between the two phases, or the concentration difference between the two phases, goes to 0. The two phases become identical in composition. The length xi, which I have denoted here as the width of the interface, will grow. In principle, it will become very large if there are no external fields that would prevent that from growing very large. And we will say, succinctly speaking, we'll say just that it diverges. And then there is the quantity, which is the free energy per unit volume, which we will follow from below criticality up till criticality. Or alternatively, we could also come down to criticality from higher temperatures. And in each of these two cases, the free energy per unit volume would have an extra part to it, which pertains to criticality and which is actually going to 0. And this extra part in the free energy per unit volume is called the singular part of this free energy per unit volume. And we will be able to calculate it in a simple model calculation a bit later on in these lectures. So I recall the density difference or concentration difference goes to 0 at criticality, and we characterize this vanishing by an exponent, which is called a critical exponent, and it carries the name beta traditionally for this density difference, not to be confused with the name of the phase beta that we used for our fluids. Likewise, there is a critical exponent for the divergence of what is called the correlation length or width of the interface. And that exponent is a negative one. And so the nu that is introduced here is a positive quantity. There is also an exponent corresponding to the vanishing of this singular part of the free energy per unit volume. And that exponent is denoted by 2 minus alpha standardly. And alpha is another critical exponent, not to be confused with the name alpha of the phase that we have introduced previously. So these alpha, beta, and nu are critical exponents. And there is a historical reason why there's this 2 minus alpha and not just some other letter. And the reason is that if you take two temperature derivatives of this delta F, you obtain the singular part of the specific heat of this system. And that is characterized typically with a weak divergence, and it would vary as T minus Tc to the minus alpha. Now, the interfacial tension, interestingly, vanishes at criticality, and this may not seem all too surprising because at criticality these two phases become identical, and so the interface between them somehow is going to disappear. And so would its excess free energy per unit area, which is the interfacial tension. So that's not a big surprise, but nevertheless, it is still intriguing to see how this vanishing comes about, because the interfacial tension is proportional to this singular part of the bulk free energy density, which is energy per unit volume, times the length in order to make energy per unit area. But this length here is in fact the correlation length. And so in a representation of the theory, which is called scaling argument, this product will determine how the interfacial tension behaves near the critical point. And now if you compose the critical exponent for the interfacial tension, you see that it is made up of two contributions. One is the 2 minus alpha, and the other one is the minus nu. And so the interfacial tension critical exponent is this linear combination of these critical exponents that pertain to the bulk quantities, if we believe this scaling hypothesis, which describes how the interfacial tension should behave near criticality. Now, in practice, the value of this exponent, mu, for fluids that are typical in a three-dimensional laboratory setting would be around 1, a little bit larger, 1.3. And it can be calculated in model calculations for models that belong to the same universality class as this experimental system under consideration. And for binary fluids of the type that we're considering, this universality class is the same as that of the three-dimensional Ising model ferromagnet. And so already here we see a hint to the concept of universality, which is the notion that many systems, although they would appear to be physically very different to every sensible person, will have behavior near their respective critical points, which could be the liquid vapor critical point, which could be the consolute point for binary mixtures, or which could be the Curie point for a ferromagnet. But at least we would have to choose an Ising uniaxial ferromagnet for that purpose. And all those systems would feature the same values for these critical exponents close to their own respective criticalities. So that's a notion of universality, which was discovered experimentally and then underpinned theoretically using the renormalization group theory, for which Wilson obtained a Nobel Prize in the early 80s. And so here we are ready now to embark on the properties of the interfacial tension and also the properties of the three-phase contact line. So I'm going to pause here a little bit and look whether there is something going on in the chat or whether there are still participants following these sessions. Let's see. Okay, I have no indication that there should be something to worry about. I'm just checking. Jane, is everything okay, you think? Yeah?
Yes, I am. Thank you.
Okay, excellent. So now we go back. So here we're going to start building perhaps the simplest possible theoretical description, the simplest possible modeling called mean field theory for as few components as possible and in as few spatial dimensions as realistically relevant to our system. So this is the absolute minimal theory that can produce some sensible, say, facts and sensible observations concerning interfaces and wetting. So we start from our free energy per unit volume, and we're going to choose a symmetric representation. That is actually the one that is used in the Ising model calculations. So in the Ising model language and the Ising model symmetry, there is perfect symmetry between liquid and vapor, and there is perfect symmetry between the two liquids in the binary mixture in such a way that we can map the system onto the Ising ferromagnet, which has perfect symmetry between up and down orientation for the magnetization, at least in zero external magnetic field. And in zero external magnetic fields, we find these two existing phases, the coexisting phases, with order parameters or magnetization values minus M0 and plus M0. And also, if we take the temperature up to the Curie point or up to the critical point of the Ising model, we would find that these values M0 and minus M0 would both tend to 0. And the way they do that is the following singular behavior. We already alluded to the density difference vanishing at a critical point, and here we have the vanishing of the Ising model order parameter or spontaneous magnetization. And in mean field theory, there is an exponent here that is called beta, as I already told you. And the value of beta in the mean field calculations is 1/2. So let's keep this in mind. For the free energy density per unit volume, we're going to choose a representation that is very much, say, practical to use in calculations. And we will take for granted the existence of the spontaneous magnetization here, which we call M0. And then below the critical point, when M0 is non-zero, we have this double parabola or the quartic shape, which is a product of two parabolae. One is centered around M0, the other is centered around minus M0. We add an external field, external magnetic field, which we will not use much for the moment, but that would allow one to go away from two-phase coexistence and to favor one of these phases, either the one with positive or the one with negative spontaneous magnetization, when we are in non-zero external fields. So then these two minima would no longer be equal minima. But for the time being, we work at zero magnetic field, so in a very symmetric setting. And now comes the expression for the interfacial tension in the form of a functional of this order parameter m. So we imagine that m varies in space across an interface between bulk values minus m0 and plus m0. So in space, we will go from the extreme left to the extreme right, and we assume the alpha phase, which could be characterized by minus m0, and the beta phase that is characterized by plus m0 to be the limiting phases, to be the bulk conditions infinitely far to the left and the right, respectively. So we integrate over space, and if we want to obtain an energy per unit area, we better integrate an energy per unit volume over length. The energy per unit volume will be taken to be as simple as possible. It has two contributions. One contribution is due to the fact that the order parameter or density or magnetization varies in space, and its spatial variation will amount to an energy cost proportional to the gradient squared of this profile. And so c squared is a positive quantity. We will assume it to be constant. It may have some dependence on temperature. It may also maybe have some very subtle singular behavior near the critical point, but we will ignore that. So this is a contribution that penalizes inhomogeneities, spatial inhomogeneities of the profile. And think of it as coming from the attractive interactions between molecules, or perhaps the energies of alignment of spins in an Ising model. If we have a ferromagnetic Ising model, then the spins tend to align parallel to one another. If we go from one site to the neighboring site. And so if we would break that kind of equal ordering, we would incur a penalty, and that penalty of course would be associated with differences of magnetizations on neighboring sites, and it would be associated with a gradient of the magnetization profile. So this has to do with inter-particle interactions. And then this contribution is what you could call a sort of more thermodynamic contribution. And this will penalize values of the magnetization or values of the density that we would try to encounter in our profile that would be different from the optimal equilibrium values that minimize F. So of course, if we want to go from minus M0 to plus M0, we have to go through values that do not minimize F, and that will entail a positive free energy cost. Suppose we would like to make a homogeneous state that would not correspond to the minima of F, then of course we would have to pay a certain free energy per unit volume, and that is this cost that is incurred here as we go along the interface. Is everything clear, Jane? Is this possible to follow this? A bit lost? Where exactly did you get lost?
Going a bit fast was when the mean field was beta equals a half, and then starting from the interfacial tension functional in this one. So it's limiting between a positive and a negative infinity as we tend towards the two sides, yeah?
Yes.
And then I got that this was the energy cost of the gradient profile. But I'm not too sure, firstly, if that isn't in right. It's not a mu. Okay. So, yeah, then these two functions. So I only understood that the first term is the energy cost and the second term is the thermodynamic contribution.
Well, both are energy per unit volume costs. One is due to the fact that there is a spatial variation of the order parameter. And so that will entail a certain cost because the homogeneous state, so the state in which locally the density is uniform, okay, is favored, because that would correspond to the molecules being at appropriate distances from one another, such as to minimize locally their energy. That's right. So this will pertain to bulk liquid-liquid mixtures or to liquid vapor systems in which if we are deep into the vapor phase or deep into the liquid phase, we would have locally a constant, spatially uniform density. Okay, and that will lead to a lower free energy. And so the second term contains entropic contributions as well. So it's not only energy contribution, but also entropic contribution. And the second term is the penalty that a homogeneous state would incur if we would put the wrong density. Okay, because if we take a homogeneous state and put the wrong density, then look at the f of m curve, we would be perhaps somewhere here, and it would have an f value that is higher than that in the minima. So any realization of a homogeneous state, spatially uniform state with the wrong density that doesn't correspond to the minimum of f, will be penalized by the value of f itself. Okay. So strictly speaking, what I have not mentioned here, and perhaps is worth mentioning now, is that I've chosen f to be 0 in the minima, so that in this second term I can omit a constant. I can omit a constant which would correspond to f in the minima. So that is not counted in the interfacial tension. So the f second term is the difference of f with respect to its value in the two minima, which I have silently set to 0. Okay. So note that those two contributions are both positive contributions. So one is due to inhomogeneity in space. The other is due to having the wrong density all over in the system. And so the cost of having the wrong density all over in the system is here evaluated locally. Because as I integrate over x, m of x will vary between minus m0 and plus m0. And so I will be integrating the area under the f of m in some sense. Not quite, because the integration variable is not m, but is x. But I could write this second term as an f multiplied by dx dm, right? So I could change the variables, and then you would see better that I'm actually integrating over this f function. Make sense?
Yes. So can we put it back to like the example for your drop? So if we were to complete this image, for example, then this part would be your droplet, and then this would be the charge.
Yeah, so coming back to the droplets, coming back to the system here, we're now looking, here is better. Yeah, or maybe this one's more clear. So here we're looking at this situation here where we go from the blue phase to the transparent phase. We're going across this interface here, which is the bulk, the interface between the two bulk phases. So strictly speaking, these two phases are coexisting only at the height in the room here, the height at which the interface is apparent. So that's where the two phases coexist. Because if I go a little bit higher up here, or I go a little bit lower down here, I'm actually introducing this external field term. And I'm no longer at exact equal minima of free energy per unit volume of these two phases. So I'm introducing gravitational bias. You see? And so if I go deep down in the blue phase here, I'm not at coexistence anymore between the blue phase and the transparent phase. I have favored the blue phase. So the blue phase is stable here and the other phase is not. But at the location of the interface, the two phases are in rather precise thermodynamic equilibrium with one another. Okay. And so if I go across that interface from one phase into the other, I'm doing what I did just right now. I'm integrating the free energy cost per unit volume and obtain the interfacial tension. So, okay, so let's go back to here. Now, what we're going to find out now together, and the reason I've explained this in some more detail here is that we need these concepts that we just try to understand. We need those concepts to obtain the equilibrium interfacial tension and to obtain the so-called optimal profile that, according to this simple density functional theory, would describe the transition from the minus m0 to the plus m0 values for this order parameter. We call this magnetization here an order parameter because the order parameter typically takes different values in the two coexisting phases. Okay, and vanishes typically when we go above the critical point. So what we're going to do is we're going to do variational calculus. We're going to minimize this functional. And from this, we should be able to obtain the profile, but also the value of this functional in the optimal profile. And that will give us the equilibrium interfacial tension, right? So that's our plan. So, okay. I'm going to outline the basic strategy here, and then I'll introduce a small break during which we can have a drink. Okay. So this this slide is devoted to what's called the mechanical analogy of this problem. It's a very handy but also a very inspiring analogy between this thermodynamic problem that we're dealing with and a mechanical Newtonian problem of a particle that is moving in some mechanical potential energy landscape. Okay, so this is an analogy between thermodynamics and mechanics, and we will see that it has some kind of dictionary of correspondence. Okay, so the Euler-Lagrange equation that we can derive rather easily from our functional. Let's go back to the functional. So you see you have here the gradient squared of a function, and here you have the f function of our function. And this is very reminiscent of a mechanical problem with some kind of kinetic energy term and some kind of potential energy. If we make the correspondence that m is position in the mechanical analogy, x is time, and minus f is the mechanical potential. So not plus f, but minus f. So the upside down of f would have two hills. And the game here is to let the ball roll from the minus m0 hill so that it would end up and come to a rest on the plus m0 hill. And as you can imagine, if these hills are exactly equal height and if we have no friction, and this would require just a very infinitesimal push on the ball to start rolling down from the minus m0 hill and to end up on the plus m0 hill. And that's exactly the mechanical analogy of our problem here. So the Euler-Lagrange equations, I trust you can write very easily. So it's a ddx of dl, where L is the integrand of our functional, dm dot, where m dot is dm dx. And the right-hand side is dl dm. And so this boils down to the Newton equation of motion, second order differential equation, which is written down here. And now you can appreciate already that F is minus the mechanical potential, right? Because the force is minus the gradient of the mechanical potential. And so what would be now our next steps after the break? So after our sort of 5-minute break, we're going to derive the profile. And also we're going to derive the equilibrium value of the interfacial tension in terms of the quantities that we have at hand here. And there's not much that we have. We have actually this m0 here, which is the order parameter, and that of course has a certain temperature dependence. So if we would be able to find the interfacial tension as a function of M0, that would already tell us something, and maybe we would find even a critical exponent if we're lucky, okay? And the profile also will tell us something about the spatial organization of this interface, and perhaps we can derive the width of the interface from this solution. Okay, so that we're going to do after the break. So please, let's introduce a 5-minute break. So I don't know if I should, we just mute? Yeah, okay. Okay, we're continuing our exploration. Okay. So in this mechanical analogy, we can understand the problem as a problem of a particle moving on a double hill potential landscape. And the first thing we're going to do is to solve our dynamical equation, or the equation of motion, subject to the proper boundary conditions, that the particle starts at minus m0 and ends up at plus m0. So let's calculate this profile. So the differential equation is basically mass times acceleration is equal to the force. And the force is this df dm. And this derivative is just this expression here, this cubic form. And the boundary conditions, we could also call them the bulk conditions, are such that m approaches minus m0 for x going to minus infinity, and m approaches plus m0 for x going to plus infinity. And so we're looking for a solution that is corresponding to this profile here. And we can verify quite straightforwardly that this differential equation is solved by this function, which is not surprisingly of hyperbolic tangents form. So it varies smoothly from minus m0 to plus m0 here. Its amplitude is m0, and we can also see, interestingly, that there is a length scale hidden in here, because the hyperbolic tangents, of course, must be expressed in terms of a dimensionless variable, and so x is a length, and so the square root of 2 times m0 over c is an inverse length. But if that is an inverse length, then the length corresponding to that quantity is the width of the interface, or the correlation length. So we can read off the width of the interface, or xi, as approximately, ignoring the square root of 2, c, which is taken to be a constant, over m0. But m0 is this spontaneous value of the order parameter, and that has a temperature dependence. So we recall that m0 varies as t minus tc to the power 1/2. So it vanishes as we approach tc. The critical exponent of m0 is 1/2 in this simple model, simple mean field model. And so we notice that the correlation length actually varies as 1 over the order parameter, and therefore it has a divergence of t minus tc to the minus 1/2. And so the exponent associated with the correlation length, which we call nu, takes the value 1/2 in this mean field description. So this is the explicit form for the interfacial profile in this simplest possible density functional theory. And it already allows one to identify, say, the critical character of the width of the interface. So that's quite interesting. And the second step now in our reasoning is to obtain the equilibrium value for the interfacial tension. And the equilibrium value for the interfacial tension is the value that the functional takes if we insert the optimal profile in the functional. And before doing that, we notice that our calculation will simplify a great deal if we use the mechanical analogy again, and we calculate the so-called first integral of the Euler-Lagrange equation, which is also called the constant of the motion. And the first integral of the Euler-Lagrange equation is obtained by taking the Euler-Lagrange equation and multiplying each side by dm dx, and then integrating between 2 points in space, like -infinity and some x bar. And if we do that, then we obtain expressions that are quite simple to manipulate. So the one on the left, we can integrate here by parts. And if we do that, if we integrate by parts, then we see that if we take the ddx from here and we move it around to here, that we get something that is proportional to the original integral. And then also the boundary contributions amount to taking the gradient squared, the dm dx squared, between the 2 points, between the 2 limits of the integration. And so in sum, on the left-hand side, we get this quantity here, which is to be evaluated in some point x bar and in -infinity. But note that the contribution from -infinity is the contribution from the far left, but in the far left, we are in the homogeneous bulk phase where there is no gradient. So that contribution vanishes. And if we look on the right-hand side, then here we obtain a very simple expression, because we have here the FDM and the MDX. And so, oh, there is 2 times the x here. That I should correct that. And so, okay, no, it's okay. It's okay. So we start from integral of f, and we go to integral of dfdm, and so then we can write, we multiply with dm dx, and so we end up with an integral which is over m, and which just has the values of f between x bar and -infinity. And so we arrive at m of x bar minus f of minus m0. But in -m0, we agreed that the value of f is 0. And so we are only left with this value of f evaluated in m of x bar. And so the constant of the motion is just c squared over 2 times the gradient squared evaluated in some arbitrary point, minus f evaluated in m at that arbitrary point, and that difference is called the constant of the motion, or the mechanical total energy, because mechanically it amounts to the kinetic energy plus the potential energy. But because of this equality here, that E takes the value 0. So this is a constraint, is a first integral that we can use in our calculation of the interfacial tension. And so what we're going to do is to use this equality in our functional. And if m wiggle, if m tilde solves the Euler-Lagrange equation, then we can use the first integral for that test profile m wiggle. And if we do that, we can replace the gradient squared contribution by the f itself in view of this identity here. And so we the integral to which this amounts is 2f integrated over x, and this equals say 2f divided by dm dx if we change the integration variable from dx to dm. Okay. So this integral is now relatively easy because we only need to integrate the square root of this function f, which is a function of m, between minus m0 and plus m0. The only thing we have to be very careful about is the sign of the mdx. So this expression is correct for the case where the mdx is positive, because we must have a positive contribution altogether. So every term in this expression for sigma is positive. And so we must always ensure that we have a positive integrand. If we would have a negative integrand, we would have to reverse the integration limits in such a way that we obtain a positive quantity. But here this is very simple. We don't have to manipulate much, or we don't have to split into different parts in space, because we go from minus m0 to plus m0 in a monotonous way with an always positive derivative. So this is fully correct the way it stands here. And the result of this calculation is very simple. It's a constant proportional, it's a constant times m0 cube. And so the equilibrium value of the interfacial tension is the third power of this m0. And this permits us to obtain the interfacial tension critical exponent, which I will address in a moment. And as you have appreciated from the previous slide, let's go back, this constant of the motion, in fact, can be exploited, and we can obtain a graphical construction from this constant of the motion. If you look here at the bottom of the slide, you see that the mdx is plus or minus the square root of 2f divided by c. So if we write the square root of an object, we always mean the positive value of this square root. And so to be completely consistent with the constant of the motion, we need to distinguish between two cases, because this constant of the motion is equivalent to these two equations, where the mdx is either plus this square root or minus the square root. In both cases, the gradient squared will be equal to f itself, apart from a constant. So this constant of the motion permits us to obtain a graphical construction, which is the following. So the gradient m dot d mdx is plus or minus the square root of 2f over c. Now f is this function. You can rewrite the product of these two parabolae in this form. M squared minus m0 squared. Now if you take the square root of this, you will have basically the modulus of m squared minus m0 squared. But if you want to take the two possibilities into account, then you have two parabolae to consider, this parabola and the upside down parabola here. And these are plus or minus the square root of 2f over c. The plus is this part here, and the minus is the part that is below the horizontal axis. Okay. So the derivative m dot has to lie, say, on these curves, provided we are following the optimal profiles as obtained from the Euler-Lagrange equation. So the Euler-Lagrange equation already selects optimal profiles in function space, and these profiles are such that the derivative versus the function must lie somewhere on these curves. Now, these curves represent possible trajectories, represent possible variations of m dot versus m. And if we choose minus m dot here on this axis, which could be a convention that's useful for us, it has the advantage that we then can discuss the interface in the upper half space of this phase portrait. Because if minus m dot is positive, we are in the upper half plane, and then m dot is actually the negative. And so we go from m0 to minus m0, okay? And that's actually opposite as what we have done here in this picture, but it is of course fully equivalent. The interface between minus m0 and m0 is the same as the one between m0 and minus m0. So if we follow this trajectory in this sense, we are actually having a negative m dot, and so we are in the upper half space if we call this minus m dot. And so it would be opposite from this picture here. Okay, now we can interpret this interfacial tension graphically, and this is something that we're going to explore now. So if we look at this picture, we can see that we are integrating this trajectory. And so we're actually concerned with the area under this curve. And so the area under this curve will be a measure of the interfacial tension between phases alpha and beta, respectively m0 and minus m0. Okay. So let us come back to our result for the interfacial tension. That is this expression here, which is proportional to m0 to the power 3. And so we see that the critical exponent of the interfacial tension is 3/2 in this mean field theory. Yeah, okay.
Okay, if we go back to 2 slides before,
Okay.
you mentioned that the energy, so the energy equals 0, that is your kinetic plus what your potential energy. Yes? And then the purple square. That is in the purple square here. That energy equals 0.
Yes.
And you made a mention that this energy is also the total energy, which can be seen as the traditional kinetic plus potential energy. But if energy is 0, then you're summing kinetic, which is 0, plus potential, which is 0. So this has no energies, which means that the c squared n squared over 2 will equal to the functional f. Correct? Okay. Then this functional f describes behavior at the interface, and so then this c, we have the. Okay, so now I'm a bit confused here by the fact that you mentioned. Sorry, there was a couple of jumps. That there's squiggly zeta, which we called the. It's the C over M0, which is proportional, sorry, the inverse length, which is correlation length. Here we go. So where exactly does the correlation length fit into this? Or is it that we use this and then we solve for it and then get something that is close to the correlation length?
Okay, so your first point is that the total mechanical energy is 0 here. So that's
Yes, that equals the
yes. So that could be of course any constant, because the potential energy, the 0 of the potential energy is now chosen exactly in the mechanical situation that the particle is at rest.
Yes, so it's chosen
Okay.
at bulk,
Yeah,
right?
that's right.
Okay.
So that's a convention. So this could have been any value, but here for our concrete situation, because of the setting of our potential, so that the top of the hill corresponds to 0 potential energy, and that's also the point where the kinetic energy is 0.
Okay, so that was when you inverse the
So
function.
by definition, the total energy there also amounts to 0, and that has to be constant all along the trajectory. So the potential energy has to become negative when the kinetic energy becomes positive.
Yes,
Oh,
okay,
okay.
okay.
And your second point concerns the correlation lengths.
Yes,
So that is actually also a kind of reasoning by induction, if you like, because there is no length present in the bulk description of the system. But here, because the argument of the hyperbolic tangents has to be dimensionless, the prefactor of x is to be interpreted as an inverse length in any case. Okay. And then we notice that the temperature dependence of that inverse length must be the temperature dependence of 1 over m0. Okay. So that implies a divergence of this length scale as you go to criticality. Okay.
So we're effectively moving from the picture, moving up here now, right? That's our movement, not because I keep thinking we're along this plane, but we're not moving up like that. Okay, I just want to see where I lost myself. So
Yeah, so the x-axis is vertical in the bottle. Okay.
okay, so the minus m. Okay, so if we take 0 to be at the interface, then minus m0 is effectively, if we look at the example of your glass bottle, the bottom of the jar, and the m positive m0 to be the top part of the jar, and those are the two different phases.
Yes, yes.
Am I looking at, okay, so then this is maybe phase 1.
Yes, in the bottles it would correspond to, say, 1 millimeter below and 1 millimeter above the interface. That would be already bulk. Sounds good?
Yes, thank you. I just got lost because I'm constantly thinking we're working now at the interface. And so
Yes, we're working very close to the interface. Very close in practice, yes. But very close in laboratory standards would be like 1 millimeter below, 1 millimeter above. But in the calculation, that would already be infinity.
Oh,
Okay. So minus infinity in the calculation or plus infinity in the calculation is like minus 1 millimeter plus 1 millimeter away from the interface. So here we see that the critical exponent of the interfacial tension turns out to be 3/2. And that's different from the 1.3 that is measured experimentally in similar systems. And that the difference is due to the fact that we've employed a simple mean field approximation in which we have expanded free energy in a very simple Taylor expansion and so on. And we have not taken into account the subtle effects of thermal fluctuations, which a better theory would take into account, okay, or a better model. So, so here, if we recall that the interfacial tension is composed of a contribution from the bulk free energy per unit volume times the correlation lengths, then the question is, what is this singular part of the bulk free energy density here in our mean field model, what would the exponent 2 minus alpha be in mean field? And we can calculate that exponent. And this is something that I would give as a homework. So find out for yourselves. Calculate this alpha using a simple Taylor series expansion or Landau type of expansion of the free energy per unit volume, close to criticality, so for small values of m. And you can take the symmetric case, so you can put the external field equal to 0, so that you can have two-phase coexistence and also reach the critical point. You have a constant A0, which is not of very much importance here. Then you have an A2 coefficient times m squared, and then A4 times m to the 4. And because of the symmetry between m and minus m, we do not have odd terms. In particular, the linear odd term is 0, okay, and also the higher order odd terms. Now these few terms, the m squared and m to the 4th, will be sufficient to permit us to calculate these quantities. For example, it will permit us to obtain the alpha exponent. And it will also permit us to obtain the beta exponent that we already introduced. We said that it was 1/2, but why is it 1/2? This will also follow from this calculation, that is homework calculation for a bulk system, not an interface, but bulk. And near the critical points, A0 and A4 can be considered to be constants. But A2, of course, has to vary linearly in first order, has to change sign across the critical point, because below criticality we have to have a double well, and so we need a negative coefficient for m squared to make a double well potential, and above criticality we just need a positive A2, because then everything is positive and then the minimum is at 0. Okay, so this is an exercise for homework, and please also calculate then the beta exponent, the exponent of m0, using these assumptions here, and basically minimize the function f as a function of m, and obtain these pieces of information. And once you have the equilibrium value for m, once you have obtained m0, so to speak, you can insert it in f and then obtain also the delta f, which is the contribution that f has relative to the critical point contribution. So that will teach you what is this 2 minus alpha. Okay. Now back to the wetting problem. Let's see how we're doing on time. Okay, I still have 10 minutes. Back to the wetting problem. For wetting, we need a third phase. We need to add at least something, because we only discussed 2 phases and their mutual interface up to now, but we need 3 interfaces. And again, our philosophy here in these lectures is not to do more work than strictly necessary to catch the concepts. And so the simplest thing we could do is to assume that the gamma phase, the one that we are adding, is almost undeformable. And that, say, the alpha gamma and beta gamma interfaces lie more or less in the same plane. Okay. Now this is not so far from the reality in this system with the liquids. If we denote the vapor phase or the air by gamma, then in fact the air cyclohexane rich phase and the air methanol rich phase interfaces lie more or less in the same horizontal plane, right? And only the interface between the 2 liquids makes a pronounced angle relative to that plane. Okay. Or let me go back to one of these earlier pictures where you also see that. So here in this system, oh, am I not sharing the screen? What happened here? No, but the others are also seeing what you're seeing, no? So I should be sharing my screen. Here it says that I am sharing the screen, so. Hi, Pellerine, are you actually there? I'm trying to share the screen now. You don't see the, do you see the presentation? No? Oh, you just have it on the side. You have to invert or something, right? But I think people can see the presentation. Yeah, okay. So here in this picture, you see that these two arrows, they are more or less, say, parallel, yes. Almost parallel. And now the idea is that we'll make them completely parallel, okay? That's the approximation we're going to make, okay? We consider them completely parallel. So that will entail, say, the situation that the third phase is actually having an angle of pi, okay? And that will simplify our considerations here. So we consider the third phase as being undeformable. It's also called spectator phase. And then this angle gamma hat is equal to pi. And of course, you can say, well, if you have a solid and you have a droplet on the solid, then of course this this angle is equal to pi, and then you have a droplet that is characterized only by one angle. Okay, so here we will consider this situation, and the alpha phase and the beta phase then sit on top of this spectator phase, and we'll consider again mechanical equilibrium of the contact line. And in this case, what we're going to do now together is to derive what is called the Young-Laplace equation for mechanical equilibrium from the cosine law for the Neumann triangle. In the limit that the alpha beta, so the fluid-fluid interfacial tension, is much smaller than either one alpha gamma or beta gamma interfacial tensions. So in that limit, if we use the Neumann triangle, we can derive the mechanical equilibrium equation that would correspond to this situation here where the gamma phase is undeformable, okay? So let's see how that goes, because if we succeed in doing that, and we consider this limiting situation, we can set up a mean field theory for wetting, which is still sufficiently simple for us to do this in these lectures, okay? So situation we are facing is, for example, one where we have an undeformable substrate and some drop on it. It could be a drop of water or maybe something else. And we're going to distinguish different states. So for example, these states are non-wet states, one with a very large contact angle, okay, almost pi. So this would be a drop on a very super hydrophobic surface, like a lotus leaf, okay? And this would be a drop on some wettable surface with a drop that shows a very small contact angle. So in this context, we can also discuss wetting. For example, the situation where this contact angle would go to 0, and this drop would spread completely over this substrate. Okay. Or conversely, we could also consider a situation where this contact angle goes to pi, and where the drop would no longer make contact with the substrate, but where, in principle, a very thin vapor layer could intrude. Okay. In principle, because gravity, of course, doesn't permit that vapor layer to become of any significant thickness. So good. So let's derive the so-called Young-Laplace equation of 1805 from the Neumann triangle concept. So if we use the cosine law, we know that the cosine of pi minus beta hat, where pi minus beta hat is this angle here, equals this combination of interfacial tensions. So I've drawn here a situation where sigma alpha beta is quite small compared to the other interfacial tensions. So let the ratio of sigma alpha beta to any one of the other, so let's call it sigma alpha gamma, for example, let it be epsilon, and let this be much smaller than unity. And note that the other two remaining interfacial tensions are almost equal to one another, if there is going to be a Neumann triangle at all, right? And these two sides are going to be almost the same. So now if we use this equation, so notice that the cosine of pi minus beta hat is minus the cosine of beta hat. And we bring the 2 times sigma alpha beta to this side. And what remains is this here. Here I've already introduced this epsilon, and it's going to give an epsilon squared in this term, which in fact is to be negligible because epsilon is assumed to be very small. And as a consequence, this difference of these two long sides is going to be proportional to this small remaining side, and it's going to be of order epsilon as well. And so this difference is of order epsilon, and so we can take the remaining factor, we can evaluate the remaining factor as if the sigma alpha beta were already 0. So we can take the 0th order for the other contributions, which means that these two are equal and equal to the one in the denominator. And so what remains to first order in epsilon, what remains is this equality, which we can rewrite as sigma alpha gamma, which is the largest one of the two large ones, is sigma beta gamma plus a small contribution. This small contribution is proportional to sigma alpha beta and the cosine of beta hat. Now, if sigma alpha gamma is indeed the largest one, then cosine beta hat is positive, but it could also be that sigma beta gamma is the largest one, in which case cosine of beta hat is negative. So this is also possible. All the possibilities actually are covered by this equation. We can go in 2 limits. We can go to the wetting limit when beta hat is 0. And you see that, as you said before, the Neumann triangle collapses in that limit, but it collapses in this inward way, so that this little piece is sigma alpha beta, and the longer piece is sigma beta gamma. Okay, but it could also collapse in the outward way, in that direction, and that would mean that the beta hat angle is pi, and then we are in a situation that like this, and this is called also wetting, if you like, but wetting by the other phase, by the supplementary phase. And in this case, it would be called drying. Okay. So, but that's a matter of terminology. So in both cases would be like wetting. One is wetting by the beta phase, and the other is wetting by the alpha phase. Okay. And then the triangle would collapse in this way. So we can derive the Young-Laplace equation, which is the equation just featuring one contact angle, starting from the Neumann triangle construction and taking the limit that the so-called critical interfacial tension is much smaller than the non-critical ones. Okay. So we've done that now together. And so the time has come to go to the mean field theory for wetting. We call it wetting at walls because we have, for simplicity, but also to cover some physically realistic situations, we have say taken the third phase gamma to be undeformable. Okay, and so one of the angles we have set to pi. Okay, so this is an approximation which is okay for systems close to criticality, where alpha and beta become critical. It's also situation appropriate, of course, if we have a solid substrate and two fluids. Okay, but then, of course, if we have a solid substrate and two fluids, we would need a more sophisticated theory to calculate those surface tensions when the solid phases are involved, because then crystals have anisotropies, and we would have to be much more careful than we are here. So here we consider this to be an approximation to replace the gamma phase by an undeformable spectator phase, which does not actively participate in the wetting properties of alpha or beta. Okay. So tomorrow we're going to go into this Landau-Degen or Kahn-Landau theory, as it is called, for wetting phase transitions. And I will also tomorrow, of course, check whether you've done the homework. Good. So thank you for your attention, and we'll meet again tomorrow. Okay.